Hey guys, welcome back to another video, and in this video we're going to be looking at this amazing problem. It states that how many 5-digit positive integers exist where the digits are non-increasing from left to right. So let's take a look at what this problem even means. 1, 2, 3, 4, 5 for a 5-digit, and it states that, for example, 87743 and 10,000 fulfill the conditions of the problem. A very easy way to understand what this means is by drawing a graph, where this symbolizes the first digit. Well, this is like the digit number, where the first symbolizes the first digit, the 2 symbolizes the second digit, 3, 4, 5. And then this is the value of the digits, where this is 0, this is 1, this is 2, this is 3, and so on until you get to 9, 7, 8, 9. Okay. Let's take a look at an example like 87743. So the first digit is an 8, so we'll draw a point here. The second digit is a 7, so we'll draw a point here. The third digit is also a 7, so we'll draw another point here. The fourth digit is a 4, so we'll draw a point right here. And the fifth digit is a 3. Okay, now drawing arrows, we can see that this graph has 3 down arrows and 1 constant arrow. Now let's draw 10,000. The first digit is a 1, and every other digit is a 0. Again, we only see constant and down arrows. And we never see increasing arrows. This leads to a very important conclusion in today's problem, which states that the left side of the integer always has to be a maximum, while the right side of the integer always has to be a minimum. Also, you've probably noticed that when there's the same integer twice, they have to be consecutive, meaning that they have to be next to each other. So let's take a look at what this really means. If you have a digit combination, like let's say you have the digit combination 1, 5, 4, 3, 2, okay? Okay, let's try and make a 5-digit non-increasing positive integer from this. We know that the first digit has to be the max, then it has to be the second max, second biggest. Third digit has to be the third largest, and so on and so forth. We can only create one. This means that because for every combination there's one non-increasing positive integer, it means that the number of combinations of digits is equal to the number of non-increasing integers. Now let's look at how many of these combinations exist. So we're going to be using a very special technique today called stars and bars. And you'll see why it's called that in just a second. But first, let's make 10 containers. These are little boxes, baskets. 6, 7, 8, 9, 10. This is container 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So each container represents a value in base 10. Right? Now let's take 5 balls. So to understand how we really work with this system, let's take the number again, 87743. This means that one of the balls goes into the 8, right? And 2 of the balls go into the 7. 1, 2. One of the balls goes into the 4, and one of the balls goes into the 3. Oh, oopsies. Yeah, so this one goes to the 4, and this one goes to the 3. All right, so now we have a way to convert a non-increasing positive integer into a simple boxes and balls scenario. But why is this called stars and bars? Well, it's called that because instead of actually focusing on the containers themselves, we're going to draw in the dividers, the bars between the containers, and we're going to not look at the containers. So 87743 looks like this. Like that, and then, all right. So this space before the first bar symbolizes the 0. This space in between the first and second bar symbolizes 1. This symbolizes 2. This symbolizes 3. This symbolizes 4. This symbolizes 5, 6, 7, 8, and 9. So now we have a way to rearrange these symbols. Rearrange them, right? Rearrange. So let's like rearrange them in a random order and see if they make a non-increasing positive integer, just so that we can prove that this method actually works. So let's just see if this even works. Yeah, okay. So remember, this is 0, this is 1, so we do have a 1 in our number. This is 2, so we have 3 2's in our number. 3, 4, and this is 5. So we have a 5 in our number. This creates the non-increasing positive integer 5, 2, 2, 2, 1. This is crazy important because, this is crazy important because it shows that all we have to do now is find how many ways are there to even rearrange this to get our final answer. So I like to think of these stars and bars as I's and O's. This transforms the whole rearrangement thing into a word with 9 I's, I, and 5 O's, right? Because this symbolizes the 5 stars or balls, and this symbolizes the 9 bars. Now, how many ways are there to rearrange this? So let's take a look at a simpler word like llama. So without duplicates, because we have 5 letters, we have 5 choices for the first letter, 4 choices for the second letter because we've already used one, 3 choices for the third, 2, and then 1. Or as you've probably seen it before, this is also known as 5 factorial. But that's not how many ways, because we have duplicates. In these 5 factorial different ways, let's number this L1 and L2, we're counting L1, L2, AMA, and L2, L1, AMA 2 different times. 2 factorial different times. So, but in reality, these two are just the same word. So we have to divide by 2 factorial to account for the duplicates of the L. We also have to divide by another 2 factorial to account for the duplicate of the A. This leads to 30 ways. So let's take this idea and put it to this word, where there are 14 total digits, 9 plus 5 equals 14, and there's 9 i's, so we have to divide by 9 factorial to account for these i's, and 5 o's, so 5 factorial. This actually leads to 14 times 13 times 12 times 11 times 10 times 9 factorial, because just 9 times 7 all the way to 1, over 9 factorial times 5 times 4 times 3 times 2 times 1. The 1 doesn't matter. 9 factorials cancel. 5 times 2 equals 10, and 4 times 3 equals 12. And you're left with 14 times 13 times 11, which is just equal to 182 times 11, which, if you calculate it, it's 2002. But this isn't our actual final answer. 2002 actually isn't final, because we have forgotten to check our work. Have we really thought about whether or not our non-increasing positive integers are 5-digit? What does 5-digit even mean? It means that this digit is non-zero. So let's take a look at how many non-increasing positive integers we accidentally included with a 10,000th digit of 0. We've already discussed that this has to be the max digit, which means that all of the other digits have to be zeros, because 0 is the lowest digit. Therefore, we have to subtract 1 to account for this accidental inclusion. Therefore, our answer is 2002 minus 1 equals 2001. non-increasing 5-digit positive integers. Thank you for watching.